Hello Advanced Physics students, this is Dr. Brinzi and this is lesson 8.2.5. In this lesson we went over describing the difference between series and parallel circuits and calculating equivalent resistance for both. So to start off class, we went through a set of whiteboards and just kind of asked ourselves, okay, let's take Ohm's law. And if you remember Ohm's law, that says that the voltage change in a resistor is equal to the current flowing through the resistor times the resistance of the resistor. So V equals I times R. So in this case, if we have a battery that is 24 volts, so that's the same thing as saying that this is at a voltage of plus 24 volts, and this side of the battery is at 0 volts. Well, if that's true, then this is also at 0 volts because this is a continuous wire leading from here to here. And likewise, this part of the wire is at plus 24 volts electric potential because this is a continuous piece of wire. So we have a change of voltage across the resistor of 24 volts. So we can write 24. And then we're looking for the current. And the resistance of the resistor is 6 ohms. So if I solve this for I get 4 amps or 4 amperes. Okay. Then we went through and calculated this missing resistance right here, and we did that using what we learned in our last lesson about series circuits. I'll give you an opportunity to practice that, and if you need to brush up on that, go ahead and watch that video. And when you're finished, go ahead and unpause and we'll go through the answer together. Okay, well, one of the things about series circuits is that the current flowing through both of these resistors is going to be the same. So there is a resistance I going through here. And actually we know what that I is because they're telling us that there are 6 amps. So this resistor will have a current of 6 amps. And this resistor will have a current of 6 amps. Because current stays constant when you are talking about resistors in series. So if I apply Ohm's law to this first resistor, the voltage drop across resistor 1 is equal to the current, which is 6, times the resistance of the resistor, which is 1.5. And when you multiply those two together, you're going to get 9 volts. Well, if that is a voltage difference of 9 volts from here to here, that means if we start off at this terminal with 24 volts, then this also is at 24 volts. And if that's at 24 volts, then this point after it is at 24 minus 9, which is equal to 15 volts. Okay. And then we know that this side of the battery is at 0 volts, so we know that the change in voltage across this resistor, delta V, or actually I should say V2, which is the change in potential across resistor 2, that's going to equal 15 volts. And if I know that that's true, then I can use Ohm's law. 15 volts equals 6 amps times our unknown resistance. And I solve for that unknown resistance, R, and I am going to get 2.5. So that's going to be 2.5 ohms. All right. So that is the value of our unknown resistance. Okay, with that little bit of refresher from last lesson, let's take a look and see if we can recognize a pattern in this table. So what we're given in this table is we are given the voltage of the battery. We are given the current that is flowing through the series circuits, and we're given the, we're given the resistance of resistor 1 in ohms, and sometimes we have a second resistor, and if that's true, that will be given by the value in this column. If there is no resistor in the circuit, then it will be left blank. So this row is a row where we have just one resistor in the circuit. Now this row is where we have two resistors in the circuit. Okay, so I want you to figure out if you can see a pattern here. Go ahead and pause the video if you need some extra time, and once you're done, unpause it and we'll go through the answer together. Okay, welcome back. So, what you may have noticed is that when the voltage of the battery and the current of the circuit remain the same, that it turns out that if you have just one resistor, that turns out to be equal to these two resistors added together. So this R is equal to that R plus that R. Okay. Well, let's take a look at the next two rows. Same voltage, same current. Here we have 1 plus 1.5 plus 2.5. That's the example we just went through. And when you add those together, you are going to get 4 ohms. Well, that's the same as this resistor right here, even though it's just a single resistor. All right, well, I'll see if you can figure out the last pattern here. If we have a circuit whose voltage is 36 volts, and if we have 3 ohms of current, or 3 amps of current, excuse me. If we have two resistors, one is 5 ohms, the other 7 ohms, what do you think this resistance will be for this single resistor? Well, hopefully you figured that out quite quickly, and that the resistance of this resistor is going to be 12, which is equal to 5 plus 7. Right. So what's the whole point of this exercise? Well, it's to actually show you that there is more than one way to get the same amount of voltage and the same amount of current. We can either get it with two resistors in series, or we can get it with a single resistor instead. And that is the principle of equivalent resistance. So these two resistors in series can be replaced by a single resistor that has the equivalent resistance. And that equivalent resistance for series circuits can be given by this equation right here. The equivalent resistance, which is this over here, is equal to R1 plus R2. So 12, equivalent resistance, is equal to 5 plus 7. Now, what do you think would happen if we had a third resistor in here? Let's say 5, 7, and 3. What would the equivalent resistance be of those three resistors in series? Well, it would be 5 plus 7 plus 3, which turns out to be 15 ohms. Okay, so we are just adding the resistance of each resistor in series, and that gives us our equivalent resistance. Okay, and you'll notice that for a series circuit, the equivalent resistance is greater than any of these resistors that you actually put in. So you can actually increase the resistance of the circuit by adding more resistors in series. Now, placing resistors in series isn't the only way that you can arrange resistors in a circuit. Here is another possible arrangement. So here, in this case, we have our battery again, but now we have, when we get up here, we can, our current, the electrons in our circuit can either choose to go this way, or they can choose to go down here and flow through this resistor right here. Actually, I pointed that out wrong because remember, in my diagram of my battery, this long line is the positive terminal, and this is the negative terminal. So actually the electrons flow from the negative terminal. So actually I should have been talking about this one down here when I'm talking about electrons. But when we talk about circuits, we usually talk about positive charge moving, even though nowadays we know it's actually the electrons that do all the moving. So that can be a little bit confusing. But anyway, back to parallel circuits here. So the parallel circuits work different than the series circuits do. Okay, when we had a series circuit, I told you that the current flowing through both resistors is the same. But this time, the change in the voltage across both the resistors is the same. So now we have something else that is staying constant. It's the change in voltage across the resistors this time. Actually, I should say across each resistor. So maybe I should actually change this to each resistor. That way we avoid confusion. So the change in voltage across each resistor is the same. It turns out that, like I said, electrons, and we'll draw them from, electrons have a choice when they get to this junction right here. Okay, they say, okay, I could choose to go up this way, or I could choose to go over this way. And some of them end up flowing this way, and some of them decide, okay, no, I'm going to move on instead. So what that means is that the current is no longer constant throughout the circuit. And it turns out that more current flows through the branch, whichever of these two branches has lower resistance. So if this has lower resistance than that, then more of the electrons will want to flow through this branch, but not all of them. Let's look at an example of a parallel circuit and how we might analyze it. So let's say I am being asked, I'm being given the voltages, I'm being given the current. So let's say, what is the current through each resistor? Maybe I'll just say, what is I1 and what is I2? Just take a shortcut. Okay, so let's call this resistor the 7 ohm. Let's call that R1. Let's call the 5 ohm resistor R2. Okay, I have a voltage of 36 volts on my battery. That is actually a voltage change between the two ends, or voltage difference. So that means that the positive end is at 36 volts, higher than the negative end. So if I decide the negative end is at 0 volts, the positive end will be at plus 36 volts. Okay, now applying one of my basic rules of circuits, I know that in a continuous piece of wire, the voltage anywhere in that continuous piece of wire has to be the same. Well, what that means is that the voltage on this side of this resistor is 36 volts. And the voltage on this side of the resistor is 36 volts because they are both connected continuously through a wire to this voltage on this side of the battery. Likewise, this is 0 volts, so the voltage on this side is 0, and the voltage on this side is 0. So both of those are at 0 volts. So hopefully you can quickly see that the voltage difference across the resistor is 36 minus 0. The voltage difference across this resistor is 36 minus 0. That's not what we had in the series circuit, was it? We had different voltages. Okay, so we can say that V1 equals V2, which equals 36 volts. That is the voltage change, or voltage difference, across each resistor. It turns out that the current is different. So we know that when electrons are here, there is a certain amount of current I going here. We don't know what that is at this time, but we know that some of it goes up here through this resistor, and we'll call that I1. And we know that some of it goes over here and travels up here through this resistor, and we'll call that current I2. Well, hopefully you can see that if we started off with I, that you have I equals I1 plus I2. If you're not 100% convinced of that, I can actually show you that that's true. Because what I can do is I can apply Ohm's law to each of these resistors, and I'm going to actually show you that. Well, actually I can't show you what I is, but let's figure out what I1 is and what I2 are. Or what I2 is, excuse me. So let's apply Ohm's law. So V1 equals I1 R1. And we know that the voltage difference is 36. We don't know what the current is, but we do know that the resistance is 7 ohms. And when we figure out what I1 is, it's going to be a number that's slightly larger than 5. It might be 5.16 or something like that, maybe. So let's round that up to 5.2 amps. Okay. We can do the same thing with our second resistor, V2 equals I2R2. We know the change in voltage across that 5 ohm resistor, again, is 36 volts. And that's going to equal I2 times 5. And for this one, we are going to get, when we solve for I, we end up getting a number that is 7.2 amperes. Okay, so I have calculated the amount of current across each resistor. Now, let's take a look here. I told you that the majority of the current will flow through the lower resistance resistor. So let's see if that's true. This is I2, or R2, excuse me. The current flowing through it is 7.2 amps. And we can compare that with the current flowing through this 7 ohm resistor, which is 5.2 amps. So it does turn out that the lower resistor draws the higher current, and the higher resistor draws a lower current through it. And that's one of the interesting things about parallel circuits. Okay, another thing that I didn't get to point out to you in class is the idea of equivalent resistance. So it turns out that I can replace these resistors with a single resistor. So it would look something like this, with a single resistor like that, and its resistance would be R equivalent, just like with the series circuits. But this has an interesting relationship. It's not R equivalent equals R1 plus R2. It turns out that it has this interesting relationship. So this is a compound fraction here, which means that what I have to do is I have to figure out what 1 over R1 is, then add that to 1 over R2, okay, and that will give me the denominator of this fraction. And then I have to take I have to take 1 over whatever that sum is to get my equivalent resistance. So, looking back at our previous slide, let's see, I know one of them was 5 and one was 7, so I would set, if I wanted to find equivalent resistance for a parallel circuit, I would have to do something like this: 1 over 1/5 plus 1/7. So I would actually have to figure out what this is first, what that sum is, and then take 1 divided by that in order to get the equivalent resistance. So let's see if we can quickly figure that out. I know that if I give these like denominators, I'm going to get 7 over 35 plus 5 over 35. And all of that is 1 divided by. And it turns out that is going to be 1 over 12 divided by 35. And if you take 1 divided by a fraction, you are taking the reciprocal of that fraction. So this equivalent resistance is 35 divided by 12. And that is just a tad under 3 ohms. We'll round it to 3 ohms to make a nice whole number. Okay, but it's a little bit less than that. Okay, so remember, we actually started off with a 5 ohm. Actually, it was in the other spot. We started off with a 7 ohm and a 5 ohm resistor. And notice that our equivalent resistance ended up being less than either of those. So in parallel circuits, you can actually reduce the equivalent resistance by adding resistors in parallel, which seems counterintuitive, doesn't it? But that's an interesting fact about parallel circuits. Okay, I want to finish up by giving you a table to help you remember some important facts about series and parallel circuits. So let's draw a series circuit here. This is what it would look like. Okay, now you notice that this doesn't look like a complete circuit with a battery in the middle of it, but you could imagine that this side and that side are hooked up to a battery with a voltage V. It's just another way of drawing the same thing that I've been drawing all along, but I want you to see that notation as well. And then this is what a parallel circuit might look like. So it has R1 and R2, but you have the electrons have an option about which path they want to travel. Okay, so that's what the circuit looks like. What remains constant in a series circuit? It is the current that remains constant through both resistors. Whereas in parallel, it is the voltage drop that remains constant between the two resistors. We can write Ohm's law for both of these circuits. So V equals IR1 plus IR2. That's another way of saying that the total voltage drop is equal to the drop across resistor 1 plus drop across resistor 2. And you can also write for a parallel circuit that the two currents add up to give you the total current I. So I equals I1 plus I2. And another way of saying that is I equals V over R1 plus V over R2. Equivalent resistance. Okay, we said when we have series circuit that the equivalent resistance is R1 plus R2. And when they are in parallel, we have this compound fraction. R equivalent equals 1 over R1 plus 1 over R2. All right, ladies and gents, that is it for lesson 8.2.4 and, oh no, I'm sorry, 8.2.5. And I will look forward to seeing you tomorrow. Bye.